All right, we're just getting everyone into the webinar, so just sit tight. We're going to start in just a minute or so. But welcome. We appreciate you spending a few minutes on a Friday with us. So just again, give folks a few minutes to join. We have a fairly large audience today, so we're very thankful for you joining us. So. While we're sitting here, we're all very excited at IWCS. We're getting within a few weeks of the deadlines for call for papers and submittal of abstracts. So I'll remind you again at the end of the webinar, but we hope that you are considering putting in an abstract and presenting the fine work that you're doing, both individually as well as your company. It's an excellent way to meet and get your information out to your peers from all over the world. So again, I hope you're strongly considering submitting an abstract to our call for papers, which is due in early April. So I can't believe how quickly the year is going by. It always seems to get faster and faster. So again, we'll just wait another 30 seconds or so to give folks time to join. All right. Well, listen, why don't we go ahead and get started? Again, I want to welcome you. Happy spring to everyone in the Northern Hemisphere anyway. It's good morning and good afternoon, good evening. And some of you, I see it's late at night, but we really appreciate your dedication to joining us. My name is Dave Cadu. I'm honored to be the CEO and director of IWCS. And a few housekeeping items before we get started. As an attendee, you are part of a larger audience. So with that, you'll be in listen-only mode. But I will also remind you that this presentation is being recorded and will be posted on our YouTube channel and accessible through our IWCS website. Typically takes a week or so to have it up and running. And so if you want to share that with your colleagues or watch it again at a later date, feel free. I encourage you to ask questions. This is a great topic today. And if you have any questions during the presentation, please submit them in the chat panel. So open up the chat and on the right of your screen, type in your question and be sure to hit the send button. And we'll have your questions asked, time permitting, at the end of the presentation. So please do that. Today, we are honored and welcome Henry Rice of Proterial Cable America. He's in New Hampshire, USA, and he is going to be presenting today on temperature cycling simulation using finite element analysis. Again, a very important component of evaluating products in our industry. This was delivered in our IWCS 2024 Cable and Connectivity Industry Forum. It was paper 8-3 back last October. Henry Rice is a fiber applications and principal products engineer at Proterial Cable. He holds a Bachelor of Science degree in Industrial Technology from the University of Southern Maine and has a Master's of Business Administration degree from the Massachusetts College of Liberal Arts. He has over 17 years of fiber optic cable design, development, and manufacturing experience, in addition to 14 years of communication cable installation and maintenance experience within the U.S. Air Force. So we really appreciate Henry for his service and also for being with us today and to present this important work. So Henry, take it away.
Thank you. So welcome. Thank you for joining the presentation today. on temperature cycling simulation using finite element analysis. I'm Henry Rice, field applications engineer with Proterio Cable America in Manchester. I'm an active BICSI RCDD. I'm an active member of the TIA and ICEA standards committees. And now I'm a contributor to IWCS. Proterio Cable America's high-performance cable division, previously Hitachi Cable America, specializes in manufacturing advanced copper and fiber optic communication cables, wireless cables, and transit cables. Our cable solutions are designed to meet the demanding requirements of industries like data centers, transportation, and infrastructure, ensuring reliable connectivity in even the most challenging environments. Today, we're going to cover the following items as they relate to fiber optic cable temperature cycle simulation. We're going to cover the question, the coefficient of linear thermal expansion, or CLTE, excess fiber length, EFL, finite element analysis, FEA, the simulation setup, the simulation results, and the conclusion. The question that every engineering team has been asked since the beginning of time. How do we improve design cycle time and reduce cost? Like every great management team, our leadership asked us how we could reduce design cycle time and reduce the number of trials to just a few to reduce the design cost and intrusion into the production schedule. And reducing intrusion into the production schedule is notably important as it affects product delivery and creates a myriad of scheduling and logistics issues. And our answer to the question was use simulation. We have played with simulation for fiber optic cable compression testing in the past, but had never used it for temperature cycling. For compression testing, it provided relative hoop strength based on material hardness, OD, and wall. The other advantage of simulation is it allows us to look at novel materials and processes and allows us to run what-if scenarios and get outside of our comfort zone and beyond the proven methods that we've used through our life. Historically, temperature cycling has been one of the hardest tests to predict based on cable design and is a key component in qualification, especially in fiber optic cables. The combination of the coefficient of linear thermal expansion, CLTE, excess fiber length, EFL, and subunit free space determines the success or the failure of the product qualification and installed use for dry loose tube cables. The specific parameter under investigation in this presentation is the finite element analysis simulation with a focus on the strain on the fibers and then how that relates to the attenuation. The coefficient of linear thermal expansion, or CLTE, as it relates to fiber optic cable, is what causes the plastic jacket to shrink along its length at cold temperatures and expand at high temperatures. This shortening of the jacket causes the fibers inside to buckle like an accordion, which increases attenuation, which reduces the amount of light transmitted to the far end of the cable. Some common CLTE applications around us include railroads, bridges, and vinyl siding. If railroad tracks are installed in cold temperatures and the rail sections are not gapped, when the temperature increases in the middle of summer, the rails can become cattywampus. Every bridge that you drove across this morning has an expansion joint to allow the sections to move with temperature. If your vinyl siding is nailed too tightly, it will buckle when it's hot and pop and crack when it's cold. The SR-71 Blackbird is a less common CLTE application, but certainly more interesting. The plane leaks fuel while it's parked on the ground because the fuel tank panels do not expand and seal until the friction of the air heats up the panels at cruising speed. The biggest contributing factor to the fiber strain and attenuation in fiber optic cables at temperature is the difference in the CLTE between the glass and the plastic. The glass has a very low CLTE, shrinks very little in the cold, and the plastic jacket CLTE is much higher and shrinks a lot in the cold. If we could build cables with materials that have matching CLTE values, then this issue would not exist. The strain that we are discussing here is not tensile strain, as in the installation load. It is the strain from the bending fibers that are pushing on each other and pushing on the jacket. Material CLTE value is generally not available from the vendor as a standard data sheet parameter. What if it was available? It's still not applicable to this use because the mechanical coupling of the components inside the cable reduces the amount of shrinkage that the plastic actually has. So for this simulation, we determine the CLTE of the subunit material empirically by taking a meter sample of cable and secured the fibers to the jacket at one end with superglue, and then measured the fiber protrusion out the other end of the cable at -40°C in the environmental chamber. The fiber protrusion length and the change in temperature was used to calculate the CLTE value for the jacket. We then utilized that value in the SolidWorks material properties for the simulation. And just for clarification, the CLTE value is not the same as post-extrusion shrinkage, which is the plastic extrusion stresses relaxing at elevated temperatures, which is permanent. CLTE is cyclical. The shrinkage only happens at cold temperatures and then expands back at elevated temperatures. Excess fiber length, as it relates to this temperature cycle simulation, is the initial state of the fibers in a loose configuration. It's the amount of optical fiber that exceeds the length of the buffer tube or subunit. It is typically expressed as a percentage of the jacket length and is unitless. It allows the fiber to be at minimal strain when the subunit is pulled or at elevated temperatures, but too much EFL at cold temperatures causes high attenuation due to the pressure on the fibers from the other fibers in the jacket shrinking from the CLTE. EFL is initially established in the subunit as a balance of fiber tension and trough shrinkage during the extrusion of the subunits. And managing EFL is much more of a challenge with dry micro distribution style cables than with outside plant gel filled cables, as the gel kind of cushions the fibers, which creates much less attenuation. Also, it is not the same as helical excess fiber length, or the helix factor, which is the fiber being longer than the jacket due to the helical stranding of the subunits. The simulation is based on 2 cable subunit samples that were measured for EFL in the lab. We then took those values and back calculated what the amplitude of the wave needed to be to determine the equation-driven line formula for the SolidWorks simulation. Adding EFL to the simulation is one of the core parameters. It makes the simulation more complicated, but provides some of the most useful information to establish the optimized starting EFL for the design. Finite element analysis predicts the behavior of an object under stress by breaking it down into smaller elements and then solves using differential equations. We're not going to go too deep with FEA here, as is a whole discipline in itself. It's often used for structural analysis to reduce design and test costs. It is used to determine the direction of a change for a design or for comparing designs rather than exact parameters due to the potential inaccuracies of a simulation. We are using FEA in SolidWorks simulation to compare our temperature cycle attenuation results from samples with different starting EFLs. We are comparing the max fiber strain values caused by the CLTE at low temperature and correlating the max strain values to attenuation. The simulation was set up to represent a short section of cable in the middle of a reel where the fiber is constrained in the jacket. The model is a 2.3 millimeter subunit with 12 fibers, no aramid, dry tube, no gel. The end faces were fixed on one end with a ridge connector between the jacket and the fibers on the other end. No penetration contact was applied between the fibers and the jacket, and a temperature load of -40°C was applied to all exposed faces. The max mesh element size was 0.0066 inches. The smaller the mesh size that you use, the longer that it takes to run, but the more accurate results that you get as it takes smaller components when it's calculating the FEA. The fibers follow the equation-driven line provided by the EFL. You can note in the picture that the fibers are parallel. We tried to randomize the fiber path, but we could not overcome the interference issues and set them in a path where they didn't initially interfere with each other. The setup was tough. Finding the right combination of connections, contact sets, and fixtures seemed like it was never going to end. My peers, Jacob Savoy and others, and the SolidWorks support line supported me through this process. And we had many failed attempts, such as remote load with fixed displacement, fibers that we rotated to be more realistic, model constraints. We had fibers popping out everywhere. The default settings in SolidWorks were not to true scale, so the exaggerated results were confusing at best. And one of the biggest challenges to this process was trying to model the aramid yarn, which I was unsuccessful at. It has a high tensile and no compression properties, and it's fibrillated with an undefined structure. But it adds volume and constricts the free fiber movement. We hope that we can refine the process better and use it in models moving forward, but it's still a challenge for us now. So we were able to successfully model an increased starting EFL correlated to increased strain, resulting in increased attenuation at low temperatures. In table 3, the strain and attenuation results, we started with 2 samples with different starting EFLs measured in the lab. We determined the max strain on the fibers at -40°C with the simulation. And then we compared the max strain values to the measured average attenuation values at -40°C. The EFL was measured in a 3 meter sample in the lab. And the attenuation change is an average of the 12 fibers over a 1 kilometer sample it's a delta attenuation between ambient and -40°C. You'll also notice that the color scale was adjusted because the jacket strain, which the jacket is hidden in this image, skewed the scale. So we had to readjust the scale to identify where the strain on the fibers themselves were being affected. And that brings us to our conclusion. The key to reducing trials from many, many iterations down to a few is simulation. And we've also concluded that too much EFL negatively impacts attenuation at low temperatures. In addition, too little EFL is a concern for tensile and high temperature during installation, also contributing to attenuation and strain concerns. Balancing EFL for low temperature and EFL for tensile high temperature is the next step to finalize the ideal design. Further validation to empirical test results are certainly necessary. This is our kind of our starting point. We feel that the model is to a place where we can start building out the data sets with other materials and other temperatures, other construction sizes, and so forth. And although the model isn't perfect, we can still continue to move forward with it. The other things that we're looking at is other materials, other sizes, and one of the things that I most want to get out of this is the correlation to multimode fiber, which historically is much more sensitive to temperature cycling than the single mode fiber that we started this process with. Thank you.
All right. Fantastic. Thank you so much, Henry. Clearly a lot of good analysis is always required in terms of forecasting performance in the field. A couple questions came to mind. One is as far as the simulations are concerned, and then selecting the environment that you test at within the environmental chamber and configurations. I know there's an infinite number of configurations that you could use, but how do you take into account long term, the Arrhenius plotting of performance so that your cycling analysis can then predict a 30-year life? How do you do that?
What I was mostly concerned about with this simulation is the qualification parameters, which really is the operational parameters. But it doesn't. I don't believe they're going to get worse over time. And in the cold, the plastic will shrink to a certain level, and it should stay at that level until it heats back up. It's not an aging issue like the plasticizers are not going to move out of the plastic. It's something that should stay static over time. So I think that once it's tested there, those values should hold over the lifetime of the cable.
And what was the temperature range again that you looked at, the low temperature and the high temperature?
We did most of the analysis here at negative 40 C, which would be the standard for an outdoor or an indoor-outdoor type cable. And it gave us enough movement in the plastic to actually see some changes. A lot of our platinum cables, the range is 0C to 70C, which is less movement, and it makes troubleshooting a little bit more difficult sometimes.
And is it relevant, the high temperature end? What was the I guess again, the temperature ratings of materials is probably relevant, but what was the high temperature range?
Typically, the high end is 70 degrees
Right.
for most fiber optic cables, but we rarely have failures at the high temperatures. It's almost always we're trying to troubleshoot failures at the low end. Because the high end is kind of covered by tensile. Like you need to have enough EFL in there to cover for tensile loading. And if you have that much in there for tensile loading, that normally covers the expansion from the high temperature.
Great. Yeah, I'm having an alarm going off here. But anyway, what was the physics that you modeled behind the thermal simulations?
I'm not sure how to answer the question. It's the coefficient of thermal expansion is like we measured how much it shrinks per degree, and that's a property of the plastic.
Yeah. What are the real life applications where dry tube cables are installed at, say, minus 40 degrees C or below? Or is that just something that takes you to simulate the degradation of the material?
The wireless cables that are going up the towers are predominantly dry tubes, and they want a temperature rating that goes down to the negative 40 C. So that's where we're typically using it. And also there's some companies I know are selling indoor outdoor dry tubes for more campus type environments and stuff of that nature.
Right. Did your model only look at tight buffer tubes? And what about what would your expectations be for loose tube configurations?
I only did it on loose tube configurations. It was a model of the subunit inside of a nanocore multi-unit type cable, micro distribution type cable. I haven't played with it with tight buffer.
Tight buffer, okay. Very good. Any possibility that you could simulate the effects of post-extrusion shrinkage, such as, the maximum strain and cable performance?
Oh, I wish. I wish.
That is a great question. That's the ultimate question.
Holy Grail.
Yeah. But is there something that you can do? I mean, obviously, post extrusion is important. That's where shrinkage could happen.
Yeah, I'm not sure that the SolidWorks simulation or FEA would be you could I'm not sure there's enough material properties or enough levers in there that you could manipulate to get an accurate post extrusion shrinkage because of it's based on the stresses that are frozen in there, and that really depends on. I know that some other people have attempted to do some analysis on it. I haven't gotten too deep into it, but I haven't found anything that I can apply to my lines to predict the post extrusion shrinkage.
Yeah, I agree with you. That's a tough one. On a practical level, what would you recommend as the balance between EFL and the impact of CLTE? For a design engineer.
So you have to put enough EFL into it so that you can cover the tensile loading, and pass the tensile and strain test, but not so much that it bunches up in cold temperatures. So if we're looking, if the question is for a very specific value, I'm not sure that I've come to that very, very specific conclusion yet. We're still getting empirical data on that process.
Is the simulation also applicable for ribbon cables, perhaps?
I would think so. I haven't played with ribbon cables, but it seems like that would be a great application for ribbon cables as well, especially since they're they're bonded together and should move, fairly consistently.
Right. And have you ever gone back and performed any testing to check how accurate the simulation was, the prediction versus the actual?
We're still building out the data set. We're not to a place yet where we're um, designing cables that we're selling. We're still filling out the data set to improve the correlation of the attenuation and the string.
But have you seen, positive results, I guess, in terms of the accuracy?
Yes, it's correlating. How accurate, like we could predict it, is pretty hazy right now. We're not quite
Mhm.
to that stage where we can have a solid prediction. But it's correlating. When the strain is going up, the attenuation is going up. So
Well, maybe that's in line for future work that you might present in some future IWCS conference, but that would be, I think that's an excellent question is how, because all these simulations need to ultimately have a validation somewhere along the line.
yeah.
So, did you actually consider stranding of loose tubes while running the simulation, or is it only straight loose tubes that you have considered?
So far, we've only dealt with the straight loose tubes. It's just as you start building layers of stuff into the model, it becomes more complicated. It takes longer to run, and there's more things that can happen. And we're just not there yet. We're trying to get it to as solid as we can with a single subunit, and then when that gets mastered, we'll go into stranded tubes and stuff.
Right. Well, good. Well, I want to thank everyone for your questions and your participation. But Henry, that's an excellent presentation, very interesting, and of course useful topic. I mean, we look forward to the further work. Please note the email address for Henry, and should you wish to contact him directly after today's event to ask more details or any questions that you might have. Um, and also be reminded that this presentation will be archived and available through the IWCS website, iwcs.org. Our next scheduled technical paper webinar event will be on Friday, April the 18th at 10:30 a.m. Eastern USA time. It's typically the third Friday of every month. Um, Again at 10:30 a.m. USA Eastern time. Each of you will be receiving an announcement for the April as well as future events. And we hope that you'll share the invites with your colleagues so they can participate in the future as well and learn of some of these really excellent innovations and items that would be very useful in our industry. Um, Please remember that as I mentioned earlier before the start, that we are actually coming close to the deadlines in April for submitting abstracts. Hopefully, you've received our call for papers, but again, we hope that you'll want to present at our IWCS 2025 Cable and Connectivity Industry Forum in October. Uh, and again, please consider submitting a simple abstract, a one-page abstract of the great work that you and your company are doing and contributing to our industry. Your perspectives is always very vital to our advancements. So a great opportunity to reach out to your global audience and your colleagues, your customers, your suppliers, again, with your important innovations. So kindly consider submitting an abstract and participating in our events this year. The deadline is coming up the second week in April, so uh, please be cognizant of that. Again, it's important. We also thank our IWCS partner sponsors. Their leadership and generosity is very vital to supporting these technology webinars and our conference, and to bring these innovations to you and our global community. So again, thank you to these leading suppliers in our industry. Our next 74th annual Cable and Connectivity Industry Forum will take place on Monday to Thursday, October 27th to 30th in Pittsburgh, Pennsylvania, USA. That's along the East Coast. So please watch your inbox and social media, as well as our website, to provide this exciting and important information as you prepare and hopefully join us in Pittsburgh. So again, thank you to Henry for today's excellent presentation and for participating today. Again, happy spring to all of us in the Northern Hemisphere. It's a relief getting away from winter, and have a great weekend. All the best. Stay healthy.
Thank you.